It's Thursday afternoon. I wanted to tell you about something else, which is about when pivot wider goes wrong and what you can do to fix it. And mostly this is a hopefully fairly short one, and mostly this is in RStudio. So I made up some data. I need to get out of the way to run this. Here's the data I made up. And you can see it's made up because the values go 19, 18, 17, 16, 15, 14. But what this is supposed to be is 6 observations of some variable y, and some of them were measured before, and some of them were measured afterwards. And they're really matched pairs, so we want a column of pre and a column of post. And so you think, alright, how am I going to get that? I'm going to go with pivot wider. And so we take D and we pivot wider, having the names come from time and the values come from y. And everything is going to go swimmingly, isn't it? No. So what happened? What happened was, here are our values of y, but there are these missing ones that came in here as well. There should be 3 post values and 3 pre ones. So what happened here? What we have to do is we have to think about how pivot wider works. And pivot wider needs to know 2 things. It needs to know what column to put each observation in and what row. The column part is easy because it uses the column that comes from names from. So in other words, when I was thinking about where to put this 19, it's going to put it in the pre column. Where I was going to put this column, this value 18, it's going to put it in the post column. 19 in pre, 18 in post. Okay, that's alright, that's no problem. That worked. But what about the rows? And there is a principle here. And that is, the way it figures out what row things go in is to look in the pivot wider and see which columns we've used. We've used time or we've used y. We've used time and we've used y. And then it looks at what is left over. What is left over? Obs. And the row it chooses for the observation is based on the distinct values of obs. And because there are 6 distinct values of obs, there are 6 rows, labeled according to obs. So that no matter what you do with your pivot wider, you're going to get 6 rows, whether you like it or not, and here you don't like it, because it's not what you wanted. Another way of looking at this is to say that there is no observation here, because there was no pre with observation number 2, was there? All we had with observation number 2 was a post. There's no pre here, so there's no value there. There's no value in pre for observation number 2. So this is a problem. This is where pivot wider went wrong. This is something you might see, and so I wanted to tell you what you can do about this. The problem here, at least, is this column obs, because it's talking about the wrong thing. These were pre and post measurements on the same people because they were matched pairs, and we've lost any identification of who is which, so we don't know which post this pre of 19 goes with. Presumably these are 2 measurements on person number 1, then 2 measurements on person number 2, and then 2 measurements on person number 3, but that's not what the data says. So the problem is with this obs column. That's why this happened. So here was where our problem was, which is just the same as we had before. There are 6 different obs values. There are 6 different rows. And there is no data, for example, for obs 2 and pre, so that cell is missing, it's empty. So we're going to have number of distinct values of observation obs rows. So we're going to have 6 rows, and we're going to have 2 columns. So there are 12 places where things can go in here. But we only have 6 numbers. So there are going to be 6 numbers in here and 6 missings. There's not enough data to fill the table we're making. There's not enough data. So obs needs to say which subject provided which 2 observations. So I fixed it up. So I changed the first column so it's called subject, and I changed the values in it to be 1, 1, 2, 2, 3, 3. So the first 2 values are for subject number 1. The second 2 values are for subject number 2 and for subject number 3. And so we have a pre and a post for subject 1, a pre and a post for subject 2, and a pre and a post for subject 3. So now we can ask the question, what's going to happen when we pivot this one wider? Perfect. Look how it worked. 3 rows, 6 observations, 1 observation in each cell, nothing missing. So this one worked just fine. And the reason it worked just fine was giving how the pivot wider was. Names from time, values from y. Names from time, values from y. The only thing that was missing was subject. So that's going to tell you which rows each value of y is going to go into. And there are only 3 different values of subjects, so there are going to be 3 different rows. These 2 values, 19 and 18, are going to go into the first row, 1 for pre and 1 for post. 19 and 18 in the first row, 1 for pre and 1 for post. So now it's going to work. And one way you can think about testing this is to say, well, I want to have 2 columns full up with 3 different things, because there are 6 observations. Or to put it another way, I know there are 2 observations on the same person. So I've got 6 observations here, but they can only be on 3 people. In other words, using the grey matter. I know they can only be on 3 people. So whatever else is in my data frame, in this case subject, has to reflect the fact that these came from 3 people. And that's why this is right. And the other one, this one, is wrong, because they weren't 6 observations, they were 3 observations times 2, 3 people times 2 to give us the 6 observations. They weren't 6 independent observations. So, knowing something about the data tells you something about what to expect. This makes no sense. And when you pivot it wider, it makes no sense. This one does make sense. This one here does make sense. And when you pivot it wider, it does the right thing. So that's how you can fix up the too little data problem. Before we move off of this one, I wanted to say something about this. There are a number of different plots you can make for matched pairs data like this. This is kind of stupid because it's kind of small, but if it was bigger, one way you could do it would be to work out the differences and then do a histogram or a normal quantile plot of those, depending on if you were looking for a general picture, which would be the histogram, or whether you were looking for normality, which would be a normal quantile plot. Another plot you can make with matched pairs data or repeated measures data in general is called a spaghetti plot, and that uses the data like this, even though that's not normally what we want, because making graphs requires things to be long. All your observations in one column, and then other columns saying what conditions they were under, pre or post, subject number. So for making a spaghetti plot, this is the format we need, which is what is D2. And I'm going to make the graph first because I've got 2 more things to talk about. Here is our spaghetti plot. So on the x-axis we have time, pre and then post. And then on the y-axis we have the observation values. And so the idea behind this being matched pairs is that these are pre and post measurements of the same thing on different people. So all of these all the post measurements are less than the pre ones. So all of these spaghetti strands are going downhill, which is a funny piece of English. The metaphor breaks down because spaghetti stands don't go downhill, but these ones do. So it's saying for each of the people, post was lower than pre. Post was lower than pre. And each one of these strands of spaghetti belongs to one person. This is actually individual number 1, number 2, and number 3. This is kind of silly for these made-up data, but for real data it would be more interesting. And so what you would see is there are some differences among people, which is kind of ancillary to what you really want to know, which is what is happening to the values of y after the treatment. And maybe it was desirable that they went down. So this is a spaghetti plot, and there are some details about how I made this. And what I'm going to do is I'm going to take that out first. Now I'll show you why that was. So we'll cut that, and we'll paste that in down here somewhere. This we're going to use as our junkyard. No, paste. Alright. I wanted to, because I didn't actually cut it. We will cut this, boom, and then we'll paste it in down here, which is our junk space. There we go. So what happens if I don't do that first thing? This is how you might think of doing it, and this is how the graph looks now. Look at the time axis. Post on the left and pre on the right. And that should offend your sense of causality, because why would after be before? That makes no logical sense at all. This should be earlier and later. So what I had to do, let's put this junkyard back. So we'll cut that out of there. We'll paste it back in where it was. There. What this was doing was reorganizing time, the time column, so it's treated in the order that it was in the data. And in the data, if we can go back and have a look at D2, pre was before post, which makes logical sense. So in other words, what makes logical sense for time is the order in which things were in the data, and that's factor in order, which is this. That would take the time to be in the order it was in the data, and not alphabetical order, which is why post was before pre. So that was one thing. The second thing was we've got to organize this graph. The time is going to be x, because the time is always x. The variable we measured happened to be called y, so we have this rather funny y equals y thing here. And then what we want to do is we want to join the observations that belong to the same person. And there's a couple of ways you can do this. Maybe color is more interesting than... Oh, I've gone into caps lock here. Color. There we go. Maybe if we do it that way, it'll work better. No, it won't, because the subjects were numbered, and, oh, yes, I have to explain this now. Subject was numbered 1, 2, 3, which was actually a rather bad choice, so I should have called them something like S1, S2, S3. But it thinks the subject is a continuous value, 1, 2, 3, anything in between, which of course is a load of nonsense. When you have a continuous variable that you're dividing into groups, so to speak, then it colors it in a shade of blue. Lighter is a higher number and darker is a lower number. So that is actually stupid. So we'll put that back the way it was. What we had was group. Let's see if we like that better. That's felt better. And what it will do is it will treat each subject as a group, so the only points it will join by lines are the ones that belong to the same subject, which is in fact exactly what we want in this case. So this is subject number 1, the values were 19 and 18, subject number 2, subject number 3. And the story you get from here is, like we said, over time the values of y are decreasing, which we hope is a good thing in this particular context. So that's making a spaghetti plot. So let's have another example, because I want to show you another way in which pivot wider can go wrong. So I'm going to make another data frame. More made up data. This is 8 independent observations, and this is a comparative study like you would analyze with a 2-sample t-test. And the idea here is that we've got 4 people going to a treatment group and 4 people going into a control group, and some variable y was measured on each of them. And then you would think about, is the treatment effective? Is the value of y significantly bigger than for control? That kind of thing. And if you were going to draw a plot of these, you might be thinking side-by-side box plots, which would make a lot of sense here, because each observation is independent of all the others. Now, suppose you did something crazy. What would happen? For example, suppose you pivoted this thing wider, so you had a column called, what you want to do is get all the control measurements in one column and the treatment measurements in another column, for whatever your purposes were in doing that. So what would happen? You would pivot this wider and you would say names from comes from group and values come from y. Alright? Names come from group, values come from y. What happens when we pivot that wider? Yeah! And what also comes with this is a warning. Values are not uniquely identified. Output will contain list calls. Well, I don't know what that means yet. We'll get to that. But so you kind of want to ignore that, but you can't ignore this because this just looks strange. So now we've got to apply the grey matter again. We did a pivot wider, so we've got to think about where rows and columns are coming from. Here's our original data. Columns are coming from here. So these 4 values go into control and these 4 values go into treatment. We're going to have columns called control and treatment, which we do. But what about the rows? The rows are determined by whatever is left over after the pivot wider. So we've used the group and we've used the y. What do we have left over? Nothing at all. So what is there to make rows out of? There is nothing to make rows out of. Everything gets smooshed together into one row. So we have one row containing this mysterious double 4. And what this actually means is that there are 4 numbers smushed together into this one cell under control, and 4 more numbers smushed together into one cell under treatment. Because everything has to go into row 1 because there's only one row. And how does it do that? This is a bit like those Russian nesting dolls. This is saying it's a cell of a data frame, but it doesn't contain just a number or a piece of text. It contains 4 numbers. It's a vector inside a cell. And this contains 4 different numbers, which is a weird thing, and it's called a list column. If you look very carefully, you can see the word list up there. A list column is a column that contains not just numbers, not just text, not just things like dates, one at a time, but it contains anything else. A collection of 4 numbers, which is the case here, or another data frame, or a fitted model object, or something of that kind. Anything that's not a single number. And this is called a list column. And the list column came because the values were not uniquely identified. In other words, we didn't know which row any of these values had to go into. They all had to go into row 1. So, this value 8 went into row 1 under control. This value 11 went into row number 1 under control, but there's already something there. This value 13 went into the same place. And this value 14 went into the same place. So there are now 4 numbers in row 1 under control. And those are these. We don't know what the 4 numbers are yet, but that's where they came from. There's too much data to fit into this data frame. We had 8 observations, and we've only got 2 cells in this data frame because we've only got 1 row. This is what happens when you have too much data. Now, you might be thinking, how am I going to get the data out? Oh, that was just to complete the warning. So that was what I meant by values are not uniquely identified. There was more than one value that had to go to the same place. In fact, there were 4 of them. And so, in the old days when we were using a thing called spread, it would just choke at this point. But pivot wider is cleverer than spread was, and it keeps hold of everything, even though it shows it to you in a rather odd way. It keeps hold of all those 4 numbers, and it says, well, the only way I know how to get them into one cell of a data frame is to make a collection of those 4 numbers and smush them all into one place, and therefore making a list column, because this thing is not just one number, it's 4 numbers together. Now, having done that, you might be thinking, well, I want to get this data out. I want to see what those 4 numbers were and what actually happened. And the standard trick for getting numbers out of a list column is unnest. And in this case, we're going to unnest the 2 columns of the list columns, which are the only 2 columns we have. And if you do that, you'll see the 4 control numbers under control and the 4 treatment numbers under treatment, which is where you wanted to get to in the first place, I suspect. I don't know why you would want to do this for this kind of thing, but the point that we're making here is that when we have 8 observations and we're trying to get them into 1 row and 2 columns, there is too much data. And the way it handles the too much data is to put the 4 observations into 1 cell, making a list column. And to get things out of a list column, you can use unnest and the names of any of the list columns that you want to disentangle. So this is the wide version of the long data frame, which we kind of don't really want, but if we had thought that we did want it, this is the answer we will be hoping to get. So I wanted to finish this by giving you a proper use of list columns. And this one is going to look a bit weird. I'll show you what it does, and I'll show you how we get to that. This is like group by and summarize. So we've got our control group, we've got 4 observations, we have a mean and standard deviation of those, and a treatment group with 4 observations and a mean and standard deviation of those, and the treatment group mean is a bit higher. So this looks like group by and summarize. In fact, it looks exactly like what you would get from group by and summarize. But this is another way of doing it, and I don't know whether you'll find this appealing or not, probably not, but it shows a proper use of list columns. So let's take this apart one step at a time. Let's take D3, which was our long data frame. No, D3 was our wide data frame. No, D3 was our long data frame, D3 was this. Losing my mind. Must be near the end of the week. This was D3. This was our long data frame. And what does this nest by group thing do? What that does is it creates a column called group with just the 2 groups in it. So in other words, it's taking this long data frame and kind of smushing it down to 2 rows. And hiding in here, it's a bit like what we had before with the list column. Slightly different layout. But we have a column called data, which is actually 2 data frames, the control group wise and the treatment group wise. And I don't know whether I can show that to you. Let's see if I can show that to you. This is a rather odd way of doing it, but this is the best way I know. Okay, so here is, we've got a column called data, which is a list column. And in the first entry in data, we have the values 8, 11, 13, and 14, which are the 4 Y values for the control group. And the second entry is a collection of 4 values 12, 15, 16, and 17, which were the 4 Y values for the treatment group. So in other words, this has got all the same information this one does. but it's actually arranged it a bit differently. We've got a column called data, which has a data frame in it, which has one column, and the one column contains the Y values for that group that we were looking at. So it looks like this. You don't see the actual values, but these data frames in here are the Y values for control and the Y values for treatment. So you have to kind of keep that in your head because you don't immediately see that. And then something else that this has going with it, which I forgot to mention but is very important, is that hiding inside nest_by is not just this reformatting that you see, but an operator called row_wise. And what the row_wise will do, which is now turned on, what that will do is to say that anything you do after this point will be done for each row individually. So what I was thinking about doing was summarizing these two rows, the control group and the treatment group, by, for example, calculating some summary stats. And there's no map or anything in here, because you would expect to map data and then some other stuff. There's no map here because of the row_wise. This calculation is going to be done for the control group and then for the treatment group. So it's like a kind of funky group by. So, what this is looking slightly different to a normal summarize. I wanted to get a sample size, a mean, and a standard deviation. And this has got to come from the data frame data that belongs to that row. So I'm going to do it for the control group first and then do it for the treatment group first. I'm going to say how many rows are there in the data in here, which would be the one for control. What is the mean of the Y in data for this, which would be for control? And what's the standard deviation of the data, the values of Y in data for the control group first and then for the treatment group first. So it looks exactly like group by and summarize. And you could do it exactly that way. This is an alternative way of doing it. And the point about all of this is actually this. The point about all of this is that this is a list column. And the things in the list column are data frames with 4 rows and 1 column, the 4 Y values in for control and the 4 Y values for treatment. And if this was a bigger data frame, it would have more columns. And so what's happening with this is for control and treatment each, row-wise in other words, it will do the calculations that we say for each of control and treatment, because there is a row-wise hidden in there. And so when you do it, it ends up looking like this. So this is a proper use of list columns, and the idea of breaking data down by groups or by models or something like that, and then doing something on each one of those, is quite a useful idea. I'm actually rather new to the row-wise, so I had to try this and see if I could get it to work. The row-wise is kind of an alternative to the map stuff that we've seen elsewhere. And as I say, run this one piece at a time to see what it does, to see that's creating you those data frames, data, which are in a list column called data. And they are everything that was in the original data frame except for group, namely Y. So I think that's as far as I wanted to go here, but I wanted to show you a little bit about list columns in the context of what goes wrong with pivot wider. So if you try a pivot wider and it doesn't work the way you were expecting, you now have some kind of context as to what is actually happening to you.